Okay. So, homework number 8 is due a week from today, and homework 8 is related to chapter 5 in the book. And that's what we're going to be talking about in some greater detail today, is the ideas behind the control volume approach and continuity. So this whole chapter kind of focuses on the idea of Q equals VA, and that the flow in and the flow out in a system can be examined, and the net difference between the two is the rate of accumulation. So we'll get into those details here in a moment, but the related assignments due a week from today. All right, so this picture is the Oahe Dam, and you can see the dam is here, this straight line where upstream is a reservoir. It's artificially produced. It wasn't always a lake here. It was just river that was dammed, and now it's the Oahe Dam on the Missouri River. And it's a project that's operated by the Army Corps of Engineers, and they have to go through a process for projects like this of assessing the benefits that are generated to justify building a big dam and justify the land that's consumed when there's a reservoir upstream of it. And the benefits that they were quantifying from this project included the ability to control flooding, because this dam has some storage capacity in it, and rather than having a big storm send a rush of water down the entirety of the river, what this can do is serve as a little bit of a cushion. Where there's a storm in the upstream watershed, the reservoir levels will go up, and so the peak downstream is modulated, and the flow rate that is released from the dam isn't quite as dramatic as it would be if this reservoir wasn't there as kind of a shock absorber for the system. So in addition to flood control, it also has some electricity generation benefits. 2,600 gigawatt hours of electricity. So that's quite a lot of power. Now this is up in the South Dakota, North Dakota region, and so there's not a lot of heavy industry out there. It's mostly agricultural, but the power serves as a big part of the electricity that's consumed in that region. So if we zoom in on this dam a little bit more, you can get a closer look at the way things are configured. There's an intake structure that takes the water from the reservoir, and under normal circumstances all of the flow goes through a tunnel to the power plant that's downstream of this intake. And there's a certain limit to the amount of water that can go through that underground tunnel, and a limit to how much water can go through the turbines that are connected to the power plant. And when that is exceeded, when there's even more water that needs to be released from the dam, then there are these overflow release gates that can be opened up. But they're not opened very often. And then as kind of a last ditch, nearly every dam has a spillway structure where, in this case, I'm not precisely sure from this view where the spillway structure is, but my guess is it's probably over here on the left, where if the water does get even higher than the flow rate that can be accommodated through the release gates and the intakes, then the water would flow over the surface rather than through underground pipes. So here's a look at the electricity generation part and the power plant. You can see that this is a relatively low head dam. Now, this isn't like out in the western part of the United States where you've got really high mountains and reservoirs that have a pretty big elevation difference between the water up top and the stream down below. Here we're just maybe looking at a elevation difference of 20 or 30 feet. But still, that's enough to generate some power. What we're going to do is look at an incident that occurred about 10 years ago. Back in June of 2011, there was some heavy rainfall in the watershed upstream of the Oahe Dam. And There was so much flow that they maxed out the amount of water that could go through the power plant. 50,000 cubic feet per second is the limit of flow through the power plant. And so the 160,000 that needed to be released through the dam so that the water levels didn't get too high, they had to send 110,000 CFS through this release, this kind of overflow release. And so 50,000 through the power plant, 110,000 through the release gates. Now, just to put it into perspective, sometimes you're not sure if 160,000, is that a lot? It seems like a big number, but cubic feet per second isn't a unit that many people have a lot of direct experience with. So I thought, just to put it into perspective, what we could do is pull open the river gauging data for the Gauley River, because a lot of people maybe have done some recreation on the Gauley, like whitewater rafting, or just looking at it. And so this is some instantaneous data that's being recorded for the Gauley River. And so in the last 7 days, right now it's reporting the depth of the flow. Let's switch that to give us the discharge in terms of cubic feet per second. So over the last 7 days, you can see that the flow rate's been below 1,000 CFS in the Gauley River. So to compare 1,000 CFS in the Gauley River to 160,000 CFS going through this dam, that really starts to put it in perspective that we're talking about more than 160 times the flow. Even if we look back through a greater time period, if we look at the last 30 days, here's some interesting peaks with the Gauley River. Does anybody have an idea of what's going on here? Like, how is it that the stream flow is so steady and then suddenly spikes like that?
Rain.
You'd think it's rain, but it's not rain. They actually have a metered release. So the Army Corps of Engineers operates the structure, and they're drawing down the reservoir for the winter. In the fall, it's a Gauley season. Maybe you've heard about Gauley season. They do all the whitewater rafting on the Gauley River in September and October. And then I think maybe Bridge Day is one of the last days during Gauley season where you could go if you wanted to in late October. Put on a wetsuit and do some whitewater rafting. And so this is them doing metered releases. And it looks like it's on a daily cycle. The days that they're releasing flow, they let it out, and then overnight it's low again. And then, people are ready to go whitewater rafting, so they turn up the water, let it run high for a while. And so this is just them drawing down the reservoir so that there's plenty of capacity over the winter when things are a little more wet. If we go back through even more time, this is looking at the last 30 days. If we look at the last year, what we're going to find is that the maximum flow rate on the Gauley River, it got pretty high. Looks like here's a brief moment where we're in the range of 30,000. Well, that was pretty temporary. Just if I put my cursor in the right spot, I thought I saw 30-something. All right, so 30,000 versus 160,000. You're getting the idea. There's one other thing that's kind of funny. I was initially trying to find some data for the Ohio River, and I did, but there's an interesting thing about it. Let me pull up the gauge for the Ohio River. There's a gauge in Huntington, but the data that I found for the Huntington gauge was only depth. It didn't have the flow rate. So I was more interested in the flow rate because we're doing this comparison between streams that we know and what was happening up at the Oahe Dam. So I found the Greenup Dam, which is just downstream a bit from here. And look at this. On October 13th, the flow rate was in the range of 22,000, 37,000. The Ohio River is a big river, right? So it's one of the largest in the United States. 37,000, and then it goes all the way up here to 22 million CFS. Do you remember the huge flood? I mean, that would have been in the news. This was October 13th, and so like less than 2 weeks ago. I don't remember like...
I remember a massive flood.
Massive flood? 2 weeks ago? No, this is just instrument error. I mean, this is bad data. This isn't anything real.
Oh.
Yeah, so, I mean, there's no way that the river was at one day 40,000 CFS and then 22 million. We'd all be dead.
Huntington flood wall just ain't gonna cut it.
No, not 22 million. We'd all be under 30 feet of water. So you just sometimes have to take data with a grain of salt and apply your reasoning. You know, like it seems all official. You know, it's a government website. You know, with a good history, but this is provisional data. So this will be corrected. You know, somebody is manually going to find the fact that, oh, the flow rate 22 million, no, that's not right. They'll sort out whatever the issue was. They may just gap it entirely and just not show the data. They may have some way of extrapolating or correcting based on gauges upstream and downstream. So just whatever sensor they were using got screwed up for a day. So that's kind of interesting. All right, so back to this Oahe Dam. So the 110,000 CFS was going through 6 19-foot diameter spillway release gates. And I've got a video to show you what those looked like. But think about 19-foot diameter. So those gates, and that's like 2 basketball stand heights. You know, if a basketball stand's at 10 feet, right? I'm such a huge basketball fan, but I do think it's at 10 feet. So double that is the diameter of these gates. And we'll watch a video of those in a second. So what does it look like when 110,000 CFS is going through a 19-foot diameter spillway release gate? So we're going to calculate in a moment what would be the velocity of flow going through that gate. But before we do, let's just get a visual here of what that even looks like. Okay, so this is looking downstream, obviously. You can see the water is pretty vigorous. The white that you see is just entrained air, where it's moving fast enough that when it reaches the river downstream, there's just so much velocity and turbulence that it's kind of swirling around and it's getting some air sucked in under the water as well. And then when the water surfaces, then you know, the air bubbles are coming up. Let me fast forward a bit because we get a zoom in on one of these. Let me lower the light so you can see that a little bit more clearly. So this is a 19-foot diameter gate. I wish someone was standing there for perspective. I mean, you get an idea from the guardrail. Your guardrails are usually tall enough to be like hip height, right? So if this guardrail is hip height or maybe a little higher, this is a big gate. You know, like this channel is quite wide. And there's a lot of energy being released there. Very vigorous. Let's zoom in a bit. Okay. Yep. The water was really moving fast that day.
That is a whole lot of water.
Yes. Yes, it is. We agree. So what we're going to do is we're going to calculate what's the average velocity. We're going to use the continuity equation to determine what's the average velocity. It looks like the water's moving fast, but you know, how fast on average? If we zoom in a little bit faster here, so fast that if you jumped in, it would really send you moving. Like a life jacket, so you know, we got to think safety, but if you jumped in, that would be a wild ride. So let's see what is the average velocity. If we just take it at face value that these really are 19-foot diameter gates, and it was 110,000 CFS. All right, so let's do this example here. Now, the equation that we've had a couple of times already, because I spoiled my big reveal, my big chapter 5 reveal, is that Q equals V times A. So Q equals V times A. And we're going to use this to find the velocity of the water that's flowing through each one of the gates. So the velocity will be the Q through one gate divided by the area of one gate. So what you need to do is determine, number one, how much flow is going through each gate, assuming that it's distributed evenly. There's 6 of them, and each one of the 6 is getting the same portion of flow rate. So first of all, what is the flow rate through each gate? meaning through one of the gates. And then what's the area of one of the gates? So let me pause for a second and give you a moment to calculate what's the water velocity here. And remember that area, if we know the diameter, area is pi d squared divided by 4. So what is the velocity? I mean, one way to measure it would be if we threw a stick in the water and we knew a certain distance, you know, if we had mapped out 50 feet and we had a stopwatch, you could just measure the amount of time it takes to go from the beginning of the 50 feet to the end of the 50 feet. So that's one way of measuring the flow rate. Another is that there are these probes that you can stick down into the water, and we could use like a pitot tube. You know, that would be another way, you know, finding the increase in pressure with the pitot tube. So you can quantify the velocity that way. This volumetric method just basically says if we know the flow rate that's going through the pipes, 110,000 in total, then that means that through each of the spillways there's 18,333 CFS. And then calculate the area. Then the velocity is the flow rate divided by the area, so 64.7 feet per second. Now just to put it in perspective, a typical rule of thumb for the velocity of water over concrete is that concrete can handle 10 feet per second fine, and there isn't going to be too much risk of scour and erosion. But if the water starts going faster than that, then it can cause damage to the concrete. So you have to be really careful about finishing the concrete with a smooth surface that isn't as prone to being scoured, reinforcing the concrete with extra steel to make sure that things are really held together tightly. Sometimes what they'll do in hydraulic applications is if they have a really fast flow of water going over a concrete spillway, for example, they may inject a little bit of air underneath the water to form a cushion to try and prevent cavitation. Do you remember earlier in the semester we talked about an incident in Russia where the electricity plant basically exploded because they had some cavitation in the turbines, and you know, it started to wobble the generator and things just blew up. So the same thing could happen here. We could have cavitation, although I mean I think the greatest risk of damage is probably to the spillway itself. So maybe it wouldn't be as catastrophic an explosion as if the generator, which is spinning really fast, suddenly pops off its axis. But still, fast-moving velocity has a low pressure. Remember, Bernoulli's equation says high velocity means low pressure. And so the water pressure is going to be reduced, at least when it's enclosed. Once it gets out into the open, the pressure takes on the same as the atmospheric. But, all right, so that's just a good illustration of the continuity relationship, that Q equals VA. So let's talk more about that. The volumetric flow rate, the V that we calculated just now was the average velocity. And the reality is that probably there's a lot of different velocities. There's not just one velocity that's happening. Let me see if I can find an overhead view of this. This side view is probably good enough. So the water that comes out in the center is going to be moving faster than the velocity that's close to the edge wall. And why is that? Why would the water in the center of the channel be moving faster than the water that's at the edge wall?
Because of the velocity profile.
Velocity profile, and why is there a velocity profile?
Because it's moving in one direction.
It's moving in one direction, but that doesn't explain why it's slower near the edge. The no-slip condition, which arises because of fluid viscosity. So the no-slip condition is saying that the fluid that's in immediate contact with the solid will have the same velocity as that solid does. And so the solid's not moving. So the water that's just in a layer that coats that wall is also not moving. And then get one layer further back from that, and the water maybe is moving a little, but not very fast, because there is some internal resistance to movement. And so each subsequent layer, the further back you get from that stationary surface, can move a little bit quicker, and the fastest velocity will be in the center of the channel. So what we just calculated was the average velocity across the entire cross-section. And that's different than the velocity at a certain point. And so here, the V bar, the V with the line above it, we use that sometimes when we're being really careful about things, just to distinguish the average velocity from the velocity at a point. And sometimes, though, usually most of the time, we don't bother to write the bar above the V. It's just we kind of know that if we have calculated the velocity from this volumetric method, then it represents the average velocity. So think into the lab when we were doing flow visualization through the Osborne-Reynolds apparatus, you know, where the blue dye was being injected and the water was going down through that tube. You calculated the velocity in that experiment. That was the average velocity across the entire cross-section. That wasn't the velocity in the center of the tube, and it wasn't the velocity at the edge of the tube. It was the area weighted average. Now we can calculate the flow rate in mass flow terms. This was volumetric, where the units are volume per time. Mass flow is going to have units of kilograms per time, of mass per time. So for instance, kilograms per second. And the way that you get mass flow is simply you multiply the volumetric flow rate by the fluid density. And so in other words, m dot, which is mass flow rate, is the density of the fluid multiplied by the volumetric flow rate. And mass flow rate's especially important when we get to chapter 6 and start talking about momentum. We'll use mass flow rate, kilograms per second, quite a lot when we discuss momentum. Now, in this velocity profile, you can see that it's flat because we're just assuming that the velocity is the same everywhere when we calculate the average velocity. In reality, the more sophisticated understanding is that there's a profile. In just 2 dimensions, we've seen the profile looking like a bullet shape, you know, where it's faster in the center and less in the edge. So, you know, the velocity is really low. It's a little bit higher. It's fastest in the middle. So now if we kind of look at it from a side view, like we are here, and a side view at an angle, you can see that it's the highest velocity in the middle, the lowest on down to 0 at the edge. And so it's caused by the pipe friction and the viscosity of the fluid and the no-slip condition, all the things that we've already talked about just a few minutes ago. And so if we know the velocity at a point and we use that velocity at a point to represent the velocity in some differential area. So we say, for example, we've measured it at this particular location and we're going to assign that velocity to this element of fluid. Then what we could do is integrate over all of the elements of the fluids. And so for all of those locations where we know the velocity and we include some differential area, then the flow rate would just be the combination of all of those. And the mass flow rate would be the same approach of the velocity at a point multiplied by the differential area multiplied by the density of the fluid. So this mean or average velocity is the flow rate divided by the area. And if we have laminar flow rate, then the velocity at the center line is double the mean velocity. In other words, the mean velocity is half the velocity at the center. So when we have this smooth, bullet-shaped pattern that's associated with just laminar flow conditions, then we could actually know the velocity at a point and use that to measure the average velocity, because it would be half. But more regularly, flow conditions will be turbulent. And so this little side view is meant to illustrate that, you know, some locations that may at this brief instant in time be more than the mean velocity, just a little bit further away, it may be less than the mean velocity. So there's the velocity at a certain location, and then this profile with the dashed line represents the average. Okay, so just to apply these ideas a little bit with some more additional practice, let's say that we have oil with a known fluid density that's going through a 50 centimeter diameter pipe. And so, of course, from the diameter we can calculate the cross-sectional area, and then the mass flow rate is 550 kilograms per second. So that's m dot. What is the mean velocity, so v bar, and what is the volumetric flow rate? So let's just practice using this idea of mass flow rate. With the given data, what's the mean velocity and the volumetric flow rate? Okay, so we need to find out v, and we also need to find out q. I guess we ought to calculate q first and then v. Maybe I'll change this, the order here. What is the volumetric flow rate and the mean velocity? There we go. That'll imply the order it ought to be determined. So let's take a look at the calculations for that. So 50 centimeters is 0.5 meters. The mass flow rate is known. The density is known. So the first thing we ought to do is calculate the cross-sectional area. So 0.196 meters squared. And then once we have that at the ready for later, we can calculate the volumetric flow rate. So it's just the mass flow rate divided by the density. And so if you look at the units that are going to cancel out there, the kilograms in the numerator and the denominator are going to cancel out. And then the meters to the cube that are down here will flip up into the numerator. So the volumetric flow rate, 0.647 cubic meters per second. And then V equals Q divided by A. So 3.3 meters per second is our velocity, mean velocity. I should have put the little bar above that for the mean velocity. All right, good practice, mass flow rate. Now, there's something our book talks about called the control volume approach. And it's a method that can be used for problem solving and analysis. And so let's talk about that for a few moments. What we're looking at is a pipe. And you'll notice that the pipe diameter is changing. So it looks like the pipe diameter is getting smaller. The direction of the pipe is changing, and it's intentional. They've done that just to imply that this control volume approach can be used in irregularly shaped conduits. It doesn't have to be like a constant diameter pipe. It could be any shape. So the control volume approach, first we start by defining a couple of things. There's a system, which is the fluid itself. And it's a certain amount of fluid. It's not just saying all of the water. It's saying a certain quantity of water is the system. So the mass of a system is constant because we're only talking about a certain amount of a fluid. And it doesn't have to be water. It could be oil. It could be air. It's just some quantity of fluid particles that what we're going to do is keep track of them. What we're mainly concerned with is their location over time. And so in order to track the system over time, what we do is we define a control volume as an enclosed space. And the control volume doesn't have to be stationary. Its location can shift over time. Its shape can change over time if needed. It can rotate. It's just that the control volume is some space that we're going to be monitoring, because we want to know what's going in and what's going out through the control volume. And the fluid, the system, sometimes the system will be in the control volume, sometimes the system may be out of the control volume. It's just, I think you'll see why we focus on the idea of control volumes here in a moment. But the outside surface of the control volume is the control surface. So we label that as CS, and the control volume itself is CV. So the outside surface is the boundary that the system passes through as it enters the control volume. All right, so the reason why we would do this kind of an analysis of control volumes and systems and control surfaces is because sometimes it pays for us to keep track of where the system is over changing periods of time. So just to illustrate, let's say that we have a pipe connected to a tank and then another pipe. And what's happening is that the inflow pipe feeds the tank and the outflow pipe drains the tank. And so there's a certain liquid level in the tank right now, and you can see that it's open to the atmosphere, and so there's some capacity for additional storage there. The liquid level could get deeper, so the mass of the system that's inside of the control volume could increase, and it would increase if the flow in was greater than the flow out. Or the reverse of that is also true. If the flow out is bigger than the flow in, then the liquid level would get lower. So what the control volume approach says is, let's just establish a control surface, these dashed black lines, and monitor where the system is going in and going out through the control surfaces, and thus how much of the system is inside of the control volume at a given time. So right now at time t, there's a certain amount of the system that's in the control volume and a certain amount of the system that's in the inflow pipe. At time t plus delta t, so that just means a little bit later, notice that the liquid level is lower. You can tell just by looking that there seems to be less of the liquid in the tank. And so what that means is that the flow out is greater than the flow in. So here in darker blue is our system. So there's lots more water in the world than our system. And so right now, this little amount of water that was inside the inflow pipe, that has been pushed into the tank. But even more of the system is in the outflow pipe during this time that's elapsed. During delta t, there's more liquid in the outflow pipe than came in through the inflow pipe, and so that is why the liquid level is lower. So we use this a lot in environmental engineering, looking at inflows, outflows, and then also sometimes there's a reaction happening inside of the tank. There may be a chemical reaction that's producing reactants. There may be a biological reaction that is breaking down pollutants. And so this idea of the control volume approach is really important for environmental engineering applications. So the water can either exit the tank or be stored. The fluid that's coming in can be stored or exit the tank. And so the system itself, the number of particles that defines the system is constant, but its locations can change over time. And so the control volume approach is just the accounting of that process. It's the in versus the out and looking at how much storage has either accumulated or been reduced. So symbolically, we could say that the mass of the system at time t is the mass of the system that's in the control volume and how much of the system was in the inflow pipe. That's just keeping track of where the system is. And then later on, at time plus delta t, so some time period later, then the control volume includes a certain amount of the system, and then the rest of it is in the outflow pipe. So basically, if we find the difference between the two, the change in mass inside the control volume is the difference between in and out. So we can express this in terms of a rate, rather than just at a certain instant in time. We could say the rate of accumulation of mass in the control volume is the difference between the mass flow rate in and the mass flow rate out. So if mass flow rate in is bigger than out, the liquid level will get deeper in the tank. And so that would be a positive accumulation of mass inside the control volume. But if out is bigger than in, then the liquid level is going to be decreasing. So think about Oahe Dam. If they didn't release a lot of water, then they were going to have the liquid level inside of the reservoir continuing to get higher and higher and higher. So the reason for the big release was they needed the mass flow rate out to match the mass flow rate in, because there was rainy weather upstream and all of those watersheds were draining to the reservoir. Now, when we do this accounting of control volumes and control surfaces and looking at the system, certain of the properties of the fluid are transported with the fluid itself. And those are called extensive properties. The extensive properties are proportional to mass, and they get carried along with the mass as it moves through the system. So the momentum of the system, the energy of the fluid moves through the control volume. But certain properties of a fluid are independent of how much there is, and they're not affected by the location. So a fluid's viscosity or its color, those properties are unaffected by how much of the fluid there is. And I've already mentioned this fact that when a fluid flows across the control surface, its properties are also transported. And this is pretty important when we talk about fluid momentum. So are there any questions so far about the control volume, control surface, and tracking process we go through? All right. So I have an in-class exercise printed out I'm going to give you. And what we're going to do is look at this specific case of the Oahe Dam in a little bit more detail. I'm asking how many days will it take to drain the lake? And so here is a schematic representation of the lake. What we're assuming is that the Lake Oahe has an area of 370,000 acres. And I think I looked that up, so that's not fictional data. It is 370,000 acres, and I think maybe I even went somewhere and found the average depth. So 63.5 feet is what we're going to assume is its average depth. So from that you can obviously calculate a volume, but just in case you're not familiar with what an acre is 43,560 square feet. Of course, why wouldn't it be? Like, just rolls off the tongue. So what we want to find out is how long is it going to take to drain the lake if we know the flow rate out. So we're going to assume this 160,000 CFS, and let's just assume that that stays constant. Even though in reality that would be decreasing, because the lower the liquid level gets, then the driving force pushing the fluid through the gates is reduced. But just for simplicity's sake, for this example, let's assume that the outflow is constant. And then there's water coming into the lake from two different spots. One is a river, and one is another upstream dam. So I don't want to say too much more about this, other than here I've defined the water density, and you're going to need that. But let me hand out this paper and give you some minutes to think and interact and do some calculations. And so there's a hint here that I'm asking how long in days. It's not going to be a few minutes to drain this lake. It's going to take days. Actually, it'll take months, but I'm asking you to calculate it in days. Okay, so you need to know the Q in from the river. Like, what's the CFS of the river? Basically, you have to calculate that. And then you need to calculate the CFS from this dam. The dam, it says it's 13 million pounds of water per minute. That's not CFS yet. So you got to use the density and then also the time conversion to get it from million pounds of water per minute into cubic feet per second. And so then you're going to know the difference between the in and the out. So hopefully out is bigger than in, because if in is bigger than out, it's not going to empty. So find the difference, and then the volume of the reservoir divided by that difference will tell you the time. All right, let's just compare solutions here. Make sure we all have the same understanding. So we need to calculate the flow rate of the river from the given data. We need to calculate the flow rate of this upstream dam that's contributing to the reservoir. We'd already know the outflow rate. So we want to know the difference. In versus out is the accumulation, or in this case, the negative accumulation, which is a reduction in volume inside of that control volume. Okay. So here's a little conceptual sketch where I'm saying I've calculated the cross-sectional area of the reservoir, and this is a real simplistic understanding. We're assuming that this reservoir is, it has like vertical walls, so that as the liquid level goes down, the area isn't changing. In reality, real reservoirs have a reduced cross-sectional area as the depth decreases. Another way to think about that is as an area floods, usually the inundation area gets larger because there's just more land area that's underwater the deeper you get. So here we're making some simplifications. You know, the thing we talked about earlier with the inflow river, assuming a rectangular cross-section for that, this vertical wall assumption for the reservoir, but the inflow at the river is 1190 CFS. And then that upstream dam that's releasing 13 million pounds of water per minute. We want to know, you know, what's the volumetric rate? That's the mass flow rate, but the volumetric flow rate we can find by dividing by this density of 62.4 pounds per cubic foot. So that turns out to be 3472 CFS. So you can see that the out is way bigger than the in. So this is going to be draining because the outflow is so much larger than the inflow. The net difference is 155,338 CFS in the negative. And then the volume of the reservoir is its area times average depth. And so finally, the time to drain will be the volume that's there. You can think of it as a big bathtub. You know, what's the volume of water in the tub? Well, it's 1 times 10 to the 12th cubic feet. And if it's draining at a rate of 155,000 CFS, then that'll take 6.59 times 10 to the 6th seconds, which is 76.3 days. Now in reality, it would slow down the outflow rate as the liquid level gets less. I mean, just similar, think about what we observed in the lab last week with the orifice equation. You know, when the liquid level is lower, then the velocity of the jet that's coming out is less. And so those big gates, those 19-foot diameter gates, there was quite a lot of water. It was flowing through there really fast, but it wouldn't flow through at the same velocity as the liquid level comes down. So that would mean it's going to actually take longer. This may be, you could think of this as a lower limit of how long it takes to drain the lake. Okay, well that's all for today. Just one last look at these announcements. The homework 8 that ties into today's topic is due next Tuesday. We have lab at 2 o'clock and 3 o'clock, and we're going to be talking about the pipe rack. So I will see you there.